Thank you very much. My name's Nick Holschuh. I'm a polar scientist. Oh, here's the clicker. I'm a polar scientist, so I bring a slightly different perspective than some of the previous talks that we've heard. But I've been working with a group of folks within iHARP to think about the question of auto-interpretation of ice-penetrating radar imagery. And, oops,
Here, just a minute. I have to share screen.
sorry. Thank you. You all set? Yeah. Perfect. Thank you.
No.
So before I get into kind of the work that we've been doing, I thought I would motivate both the technical challenge and the science goal that underpin this project. And the technical challenge is one that kind of spans all kinds of image interpretation, which is how do we actually improve algorithmic or machine learning approaches to image annotation, especially when we have very limited ground truth data. Because we really want to be able to avoid the logistically intensive manual annotation of radar imagery that has been the approach of the past. And the reason we want this large annotated image data set is because if we have some integrated picture of the structure of Earth's ice sheets, we can use that information to improve projections of future sea level rise. So to give you a sense for how and why we might do that, if you didn't already know, glaciers and ice sheets are layered. So if you think about this like a cross-section of a glacier, where this is distance and this is depth, year after year, new snow falls at the ice sheet surface, and that snow is chemically distinct because soluble and insoluble impurities in the atmosphere change through time. And so each year, a new layer of snow is added. That snow is buried and it flows out to low elevation and low latitude where it melts. The shape of all of these layers within the ice sheet are a product of physical processes playing out within the glacier. So their geometry depends on what's happening in the atmosphere, the snow accumulation pattern, and how it's redistributed. It is affected by the properties of the substrate, what controls and enables fast ice flow or slow ice flow. It depends on the structure of the glacier and the forcings at the margins. So there's a lot of information potentially contained in the layer structures of glaciers. Got it. At the same time, ice sheet models, which are trying to make projections of future sea level rise, are trying to reproduce lots of these processes, but they're trying to reproduce them based on unknown properties of the physical system. And so lots of these same things that control the geometry of layers within ice sheets, like the snow accumulation pattern, the substrate geometry, the material properties, the crustal heat input, those are also necessary inputs into models, and they're unknowns. And so as kind of computational power has improved, lots of different approaches to include data to constrain models have been explored, some of which use large ensemble exercises where an ice sheet model takes a bunch of different unknown input parameters, explores the full parameter space, and then based on the agreement of the output with data, calls the results to just those that are most reasonable. Other approaches try and formally ingest those data into the model via inverse methods. But this demonstrates the possibility that layer information could be used to constrain a model to improve its projections, to improve our understanding of these unknown parameters. How do we get layer information from glaciers? That comes from ice penetrating radar data, which is what I spend most of my time thinking about. So again, if this is a cross section of a glacier, you can't quite see it on here, but here's the glacier surface, and here's us sitting at the glacier surface. What a radar does is it sends out a pulse of light, an electromagnetic wave in the radio frequency spectrum. And where there are these distinct layers within the ice sheet, some of that light is reflected. And so you're sitting at the ice sheet surface measuring the strength of those reflections through time. And if you know the speed of light in ice, you can use the time delay associated with that propagating wave to map out the geometry of the subsurface. So you drive your radar along the surface, you collect a bunch of these different time series, which are represented here. When you encode that time series information as color, you get an image, and that's what a radar image is. And you can see this is a radar image from, I think, East Antarctica, where there's this nice layered structure that reflects that history of accumulation and ice flow. And in an ideal world, we could give these images to a computer and it could identify the geometry of these layer structures within the ice. There have already been modeling exercises that try and ingest layer information formally. And there's this great example of a modeling study in East Antarctica that tried to constrain these unknown parameters, but they were really data limited. They only had a few annotated radar grams that were their basis for constraining those parameters. And so our dream is to extend that to the full radar archive, for which there are tens of thousands or hundreds of thousands of radar images. So, recognizing we have this technical challenge motivated by the science goal, we are trying to improve the products of algorithmic or machine learning approaches to image annotation. And so I'm going to talk you through a little bit about our approach and how it differs from existing approaches. So, by way of example, there's kind of a proliferation of algorithmic or machine learning approaches to try and trace these layers. And once they have layer output, it's very hard to evaluate the quality of that layer output. It's also true that for each of these approaches to annotating these images, there are choices made by the annotator. It might be parameters in an algorithm. It might be pre-processing of the image. It might be the size and scope of the training data that goes into the machine learning approach. And it's hard to evaluate which parameter choice is best, which pre-processing approach is best, which training data set is best. And so there's a really strong need to develop approaches to validating the output of these auto-annotation schemes. Even within iHARP, there are a couple of different approaches that have been taken. The two most common are that you compare the output with ground truth data. And that seems like maybe an obvious approach. It has lots of very clear benefits because we know that the ground truth data are good. When you have a manual annotator sit down and trace layers, we know the quality of those layers is good. The other approach is to simply evaluate the output using descriptive statistics. Qualities that we know are things that we desire in the output. We want the layers to be continuous. We want them to be numerous. We want them to densely sample the image. But again, each of these has limitations. The limitation associated with comparison with ground truth is that our ground truth data are incomplete. Plotted on the right is the best available data set in the world for layer annotations. Mark was involved with it. Joe McGregor spent the better part of a decade with an army of undergraduates tracing layers in Greenland. And even that, our absolute best data set, doesn't sample all of the layers within any individual image. And so if you're testing your output of your auto annotation scheme against just the annotated layers here, there are additional layers in those images that aren't present in the ground truth data set. And so that comparison is somewhat limited. The other approach, using just statistical descriptors for the layers, helps us identify things that we like, but they tend not to be unique indicators of layer annotation accuracy. Just because layers are continuous and numerous doesn't mean that they were real, that they represent some truth in the underlying image. And we find lots of these auto annotation schemes actually produce layers that we know are not real. And they span across areas where there's no signal in the underlying image. So we're trying to think about what are ways that we can get around the fact that we'll never have a complete ground truth data set, and the existing statistics are limited in their capacity to judge layer accuracy. So we're thinking about how we might leverage not just a single image to evaluate a layer, but the whole archive of annotated layers across all of either Antarctica or Greenland. And we rely on this truth, that these layers in radar data are really slices through a continuous surface. So if this color code is the elevation of the surface and you drive 4 radar layers across it, we should see a layer in each image that intersects at the intersection between those images. And so now, by comparing the product of auto annotation schemes across images, we can start to build what might be a slightly more robust metric for the quality of the layers that have been identified. So we've been using graph theory. Graph theory lets us kind of sort the data into these nodes and edges, where every individual radar image collected in Antarctica or in Greenland is a node, and every other image that it intersects with is an edge. Recognizing that if we find a layer in one, ideally, we should be able to trace it across those edges into other nodes. The idea is that layers that can be mutually identified in intersecting images are more likely if the auto annotation scheme reflects the truth of the data. because the truth of the data is that there should be intersecting layers at all of these images. It becomes increasingly unlikely that you'll be able to trace a layer through multiple images by chance. So if you have an auto annotation scheme that generated 2 random layers, maybe they have an intersection at one image, but it's very unlikely that you're going to be able to trace that same layer through the full intersecting graph. And so we applied a bunch of the existing ground truth independent metrics to auto annotation schemes, and we found that they actually weren't good predictors. They couldn't tell the difference between ground truth data and auto annotation data. And in fact, some of the auto annotation data we knew to be bad scored better than the ground truth data that we knew to be good. But as we started to approach this problem using this mutual intersection framework, what we found is that this ends up being a more robust predictor of the quality of the layering of a particular approach. So we just picked 13 images that have a single intersection at either edge. We looked at the layers that came in that state-of-the-art ground truth data set and the layers that came out of one of the auto annotation schemes. And we can start to see that we have we have a much stronger ability to consistently trace layers through these intersecting images in our ground truth data than we do in the we know to be faulty auto annotation scheme. So with this as kind of a first step, our goal is really to look through the full archive of radar imagery kind of uniformly and together, so that we don't interpret the quality of annotations in any individual image, but we leverage the power of the full data set to judge the quality of layers across Antarctica or across Greenland. So we've just got the code developed to start doing this at larger scale, with the hope that we can start to judge the quality of different auto annotation schemes. We can judge the optimal parameter inputs and the optimal pre-processing for radar imagery to try and generate the best auto annotation product. That's where we are there. If there are any questions, I'm happy to take them.
I just had a question. You want to use the full data set, and I know that spans a lot of different years. Are there any challenges that will come with using different years, like or over decades, with the layer tracing in 3D?
Yeah, so I guess is the question, there are a couple of ways I might think about that question. The actual nature of the radar instrument that was used to image the subsurface changed through time. And so image quality varies and the resolution of the system varies based on, when it was collected. So that is one complication. How do you deal with the fact that the actual underlying data are slightly different? And one thing that you can do is actually reprocess some of the old data to bring them closer to alignment. So if you have a broadband radar system in one year and a narrower band radar system in another year, you can actually down select your higher quality data and only compare them at the scale of the worst data, for example. If your question is more about, do we expect there's some evolution of the subsurface over the time scales of observation? I think it's still a safe assumption that if you collected data in 2001 and collected data in 2020, based on some tolerance, you should still see intersections of these layers across those two images. So there are certainly complications associated with the fact that we have this very heterogeneous data set. But one of the things that we're kind of thinking about is how do you creatively and intelligently deal with that heterogeneity, but try and leverage the full data set as opposed to do each piece in isolation.
Yeah, okay. So I'm Guangqing from Penn State. I'm a social scientist, so I don't really understand the technique here, but it's fascinating. My question is, when you mentioned that there are not enough ground truth data, like, can you just give a general sense, like to what extent it's good enough? Is, I think about like the scientific, the funding support, like to what extent would be just enough?
It's a good question, and good enough and not enough ground truth data is kind of an imprecise thing for me to say. I think this image that's on this slide is actually a pretty good example. So this is an example of one of the annotated images from Joe's product. And in it, you can see that it does do a good job of sampling much of that image. But there are layers in that image that could be traced that are spatially less complete than the ones that he has traced, that one may want an auto-annotation scheme to identify. And so if I just said an auto-annotation scheme is successful if it reproduces those layers, that's not really my goal. We actually want the computer to do better than the human has done because it's too logistically intense for someone to trace literally every line in every image. Because many of them are spatially discontinuous. And so you may think there's no real benefit for me to trace a layer that is maybe right there if I can't see it in another image, if I can't extend it outward. And so there's an incompleteness to it that is different from it being just insufficient in number. But it's an interesting, maybe more philosophical question. How much ground truth is enough to justify saying that an auto-annotation scheme is good? I think right now I'm more concerned with the limitation of the existing data, which I want to reiterate was the product of a Herculean effort. I cannot aspire for a better data set, really. And yet we're hoping that a computer can do better than we can. And that is where there's this interesting difficulty.
So it's a really nice spatiotemporal approach. So you're looking at images from different time snapshot, right? And then trying to leverage that. And for a static phenomena, that makes perfect sense, right? But this case, things are moving. So do you need to account for the motion when you take something from 2020 and 2000 to match it up?
So the timescales that are relevant for end glacial deformation for most of the ice sheet are too long to matter for the observational record. There are maybe some places where the evolution of the layering could be visible. And there's all kinds of technology development to try and map that time evolution of the system. But it's typically below the resolvability of these radar systems, that just in time, you don't see as much motion of the layers as would be required to kind of decorrelate them. There are in places in the ice sheet where it's deforming very rapidly and the ice is flowing very quickly. When you've got 20 years, maybe you might increase the threshold required to compare data. But it also happens that in the places that are really dynamic, the quality of the radar imagery also goes down. And so annotating images at the outlets of our most active glacier systems, like you saw an image that Bayu presented that showed an ice shelf over here on the left, I couldn't see any layering in that data. And that's typically true where there's lots of surface clutter, where you're in the ablation zone in Greenland. Tracing the layers in these really dynamic regions, a human can't do, and I have very little faith. Well, I think it would be very difficult for a computer to do because the signal is simply not in the data. So I think it is not an unfair assumption to say that in the layers in the areas where we have nice, readily traceable layers, we can treat it as quasi-static.
So thank you so much to this